Alright folks, we're getting close to the end of chapter 2, so the next part of this chapter is going to be about the macromolecules. So we'll go through, the next part of this chapter is going to be about solutions and buffers and pH. Solutions, buffers, and pH. Alright, so let's start with this. A solution is composed of two components, a solvent and the solutes which are dissolved in the solvent. So a solution is, again, two things, a solvent and the solutes dissolved in the solvent. In biology, it's pretty easy. The solvent's always water. Now, that's not always true in other disciplines. In organic chemistry, in fact, your solvent is rarely water. It's usually methylene chloride or chloroform or petroleum ether or something like that. But in biology, the solvent's water. And then the solutes are the molecules and ions dissolved in the solvent. And in human anatomy and physiology, these solutes are pretty consistent. We'll talk about the electrolytes and the other metabolites that are dissolved in our aqueous portions of our body. Please recall that water is a polar molecule. The oxygen, the end of the oxygen is partially negative. You can see that right here. And please remember that the hydrogens on water are partially positive. Because of that, water makes hydrogen bonds. I can have a hydrogen bond right here. Hydrogen bond right here. Hydrogen bond right here. So water makes hydrogen bonds. And in addition, water makes hydration spheres around things that are polar and or charged. Now remember, polar means partially charged. Like the water molecule is polar, partial charges. And charged means it has a full charge. Because water itself is polar, it can make hydration spheres around cations. How does that happen? If you look at this cation right here, the partially negative oxygens orient towards the positive sodium. It can also make hydration spheres around an anion, like this chloride right here. How does that happen? The partial positive hydrogens orient towards the anion. Opposite charges attract. So these are called hydration spheres, and this is in fact how things dissolve. This is dissolution. This is how sugar and salts dissolve in water, is through these hydration spheres. Alright, so that's a solution in hydration spheres. Water is a very important molecule, and it has a couple properties that are unique. So let me point a couple of these out. First of all, it has this heat of fusion right here. This heat of fusion right here. Alright, what does that mean? Well, we have a constant temperature of 0 degrees Celsius. At 0 degrees Celsius, when I'm not changing temperature now, that's the key here. At 0 degrees Celsius, I could be a liquid or I could be ice. I could be either one at 0 degrees Celsius. If I'm ice and I become a liquid without changing the temperature, I must absorb 80 calories of heat, and that's the heat of fusion. Now notice I absorbed energy but didn't change temperature. Where did the energy go? It went into breaking the frozen hydrogen bonds, the ice, into the liquid, but I did not absorb enough energy to change temperature. That's called the heat of fusion. Likewise, I have a heat of vaporization right here. At one temperature, 100 degrees Celsius, water can exist as the liquid form or as the gaseous form, steam. Now I'm not changing temperature. If I'm at 100 degrees Celsius, I'm liquid water, and I absorb 540 calories of energy, I become gaseous water, steam, vapor, water vapor. Now I didn't change temperature. I didn't absorb enough energy to change temperature. I simply absorbed enough energy to change from liquid to gas without changing temperature. So this heat of fusion and heat of vaporization, they're quite high compared to other compounds, and this is one of the reasons why sweating cools you off so well. You have a bead of liquid sweat on your forehead, and you're running, and the heat of your body changes that liquid to steam, and when that water evaporates from your forehead, it takes with it 540 calories of heat. It cools you down. This is how sweating cools you down. Alright, now what about in here from 0 to 100? Well, in there, I have a straight line, as you can see. And the relationship that I have between 0 and 100 in the liquid form is the amount of energy it takes to change 1 gram of water, or 1 milliliter of water, which by the way weighs 1 gram, 1 degree Celsius is 1 calorie. 1 calorie is required to raise the temperature of 1 milliliter of water 1 degree Celsius. That's the definition of a calorie, by the way. The amount of energy required to raise 1 milliliter of water 1 degree Celsius. And by the way, it's at a certain pressure too, and I forget, maybe 1 atmosphere, 760 torr. So I don't remember that, but that's the definition of a calorie. All right. So that's water. Let's talk about intensive and extensive properties for a second. And what do I mean by that? Well, before I tell you what I mean, let me ask you a question. If I have a glass of water, here's a glass of water, and this glass of water is a nice cool glass of water at 4 degrees Celsius. No. Let's not make that 4 degrees Celsius. This is a warm glass of water. I'm going to make tea. This is, let's call this just under boiling. Let's call this 96 degrees Celsius. Just under boiling. So it's not boiling, but it's hot. All right. And I have the Atlantic Ocean. And the Atlantic Ocean is 50 degrees Celsius. No, 50 degrees Fahrenheit maybe, not 50 degrees Celsius. Atlantic Ocean is 15 degrees Celsius. Just so you know, 25 degrees Celsius is room temperature, 37 degrees Celsius is body temperature. So this Atlantic Ocean is far less than room temperature. Okay, and 0 degrees Celsius is freezing. Okay, so my Atlantic Ocean is 15 degrees Celsius, and my glass of water is 96 degrees Celsius. All right, who has more heat? Who has more heat? Let me take that question back. Let's answer that in a few seconds. Who has the higher temperature? Easy. Glass of water has the higher temperature, 96 degrees Celsius. Now, who has more heat? And the answer is the Atlantic Ocean has more heat. How can the Atlantic Ocean have more heat? Its heat is the amount of energy in the entire body of the Atlantic Ocean. And the 15 degrees Celsius is a measurement of just the temperature of it, not how much heat is in the entire body of the Atlantic Ocean. So temperature is, could I say average heat? I'm trying to think. Can I say temperature is average heat? Don't know, but temperature is how much, yeah, temperature is average heat. Temperature is a measurement of average heat, not total heat. So there's more energy in the Atlantic Ocean than there is this glass of water, even though the glass of water has a higher temperature than the Atlantic Ocean. Hope that makes sense to you. And this has to do with the intensive and extensive properties of matter. Intensive properties are independent of the amount of matter, of amount of matter. And extensive properties are dependent on amount of matter. And you could look at something and you could say that you could say the mass is an extensive property, but the density is not. So how much something weighs, the mass, of course the mass is extensive property. It depends how much is there. But the density is grams per volume, and that's independent of how much is there. say grams per milliliter. If you check the density of just this little corner of this block, it would be the same density if you checked the density of that little corner, and it would be the same density if you checked the whole entire thing. So it would be independent on the amount. So intensive properties are independent of the amount of matter, and extensive properties are dependent on the amount of matter. All right, in solutions we have these recurring, in a human body we have these electrolytes, and they are the homeostasis of these electrolytes is tightly controlled. Some are tighter than others, but they're relatively tightly controlled. So we have normal ranges for all these electrolytes. And the biggest things I want you to memorize right now is this. Sodium is a major extracellular cation. Extracellular cation. Potassium is a major intracellular cation. Chloride is a major extracellular anion. And phosphate is a major intracellular anion. You absolutely have to memorize that. Now, is that what this graph shows me? Sure. Plasma and interstitial fluid between the cells, is extracellular. It's outside the cells. Intracellular is intracellular. So look at intracellular. Is there much sodium intracellular? Nope. Is there much potassium intracellular? Yep. Potassium is a major intracellular cation. Let's look at the anion intracellular. Is there much chloride intracellular? Nope. Is there much phosphate intracellular? Yep. Phosphate is a major intracellular anion. Let's look at extracellular. Is there much sodium extracellular? Yep. Sure is. Tons of it. Is there much chloride extracellular? Yeah, there is. Is there much potassium extracellular? Nope. Is there much phosphate extracellular? Nope. So, electrolytes are anions and cations that float around our body in solution, both inside our cells and in our blood plasma and in the fluids between our cells. And you need to memorize that sodium is a major extracellular cation. Potassium is a major intracellular cation. Chloride is a major extracellular anion, and phosphate is a major intracellular anion. If you memorize that now, it'll come back and pay you dividends in the future. We will come back to that concept. And by the way, this graph is found in chapter probably 26, 27, something like that. And this will come back and pay dividends if you memorize that. Similar type of graph. The maroon and blue are extracellular fluids. The yellow is intracellular. So if you look at sodium, you see maroon and blue, extracellular. If you look at potassium, you see yellow, intracellular, and so on and so forth. Similar type of graph here. All right, pH. pH is the negative log of a hydrogen ion concentration. So negative log of hydrogen ion concentration. The brackets mean concentration. Another way of writing negative log of hydrogen ion concentration is 1 over the log of hydrogen ion concentration. All right. Now this is why the pH scale is a little bit counterintuitive. If I said the hydrogen ion concentration was 10 versus 1, you would say, yeah, 10's higher than 1. Okay. But is 1/10 higher than 1 over 1? No, it's less than 1 over 1. But 10 is greater than 1. So the pH scale, you become more acidic as you go down, because pH is the negative log, or 1 over the log of hydrogen ion concentration. And because the hydrogen ion concentration is in the denominator, the pH scale is inverse, meaning the more hydrogen ions you have, the more acidic you are, the lower your pH value, because the hydrogen ion concentration is on the bottom of the fraction. It's the denominator. All right, so that's why the pH scale is a little bit counterintuitive. The lower the pH, the more acidic. The higher pH, the more basic or less acidic, you could say. pH scale runs from 0 to 14. 0 being the most acidic you can be, and 14 being the most basic you can be. So that's the pH scale. A couple more concepts here. Neutral is pH 7. However, you absolutely must memorize that normal body pH is 7.35 to 7.45. This is blood and interstitial fluid, all extracellular fluid, even intracellular fluid except for one thing. Except for not lysosomes. An organelle, which is actually acidic. But most of the fluid in your body is 7.35 to 7.45. There is one exception, that's the lysosomes. They are these acidic organelles we'll talk about in the next chapter. All right, having said that the normal body pH is 7.35 to 7.45, I'm telling you that normal body pH is slightly alkaline, just slightly basic. So what happens if the pH of your body is 7.1? Well, first of all, you're close to death. That's how tightly we keep this variable in homeostasis. If your body has a pH of 7.1, is that acidic or basic or neutral? Well, it's slightly basic, but we call it acidosis. Well, why the heck would I call 7.1 acidosis if it's slightly basic? Because normal value is 7.35 to 7.45. Anything less than 7.35 is considered acidosis. Anything greater than 7.45 is considered alkalosis. And yeah, strictly speaking, 7.1 is not acidic, but it's acidic for normal value, so we say it's acidotic. Alright, so that was a concept I wanted to mention to you. Buffers.
A buffer is an aqueous solution containing both a weak acid and a weak base that are a conjugate acid-base pair. The buffer shown contains the weak acid acetic acid and its conjugate base acetate. These species are dissolved in water. Water molecules are not shown in this animation to draw focus to the buffer components. A buffer solution has the ability to resist changes in pH upon the addition of small amounts of either acid or base. Choose to add a strong acid or a strong base to the buffer by clicking one of the buttons.
Okay, so I don't care what test you're going to take. PCAT, MCAT, NCLEX, whatever it is. I don't care what it is. You need to understand that a buffer resists pH change. That's going to be the answer on your test. Your test is going to say, what does a buffer do? And the answer is a buffer resists or prevents, or whatever word they use, pH change. And here's how a buffer does that. A buffer is a mixture of compounds that have the ability to donate a proton, a hydrogen ion. Remember what a proton is. It's a hydrogen ion. That's an acid. It has the ability to donate a proton or accept a proton. Well, how do I know which ones the buffer is going to do? It depends what the pH of the solution around it's doing. If the solution is becoming too basic, the buffer donates a proton and it brings the solution back to normal. If the solution is becoming too acidic, it accepts protons and the solution comes back to normal. So let me add a strong acid. Before I click that, let me tell you what should happen on this graph. If I add a strong acid to this beaker, so what I'm really saying to you is I'm going to take H plus and put into that beaker. All right, that's what I'm saying. This acetate should accept those excess protons. So acetate will go down, my green graph will go down, and my purple graph will go up because the acetate becomes acetic acid. Why did the acetate become acetic acid? Because the acetate's being protonated, or the hydrogen ion is being added to it to become acetic acid, but it's buffering the pH. So let's go ahead and do that.
Only hydrogen ions, H+, from the hydrochloric acid are shown entering the solution. Chloride is not shown because it is a spectator ion. It does not participate in the reaction. The strong acid H+ reacts with the base component of the buffer acetate, CH3COO-, producing the acid component of the buffer acetic acid, CH3COOH. The buffer has resisted a change in pH by removing strong acid, H+, from the solution.
Okay, now let's add a strong base.
Only hydroxide ions, OH-, from the strong base sodium hydroxide are shown entering the solution. Sodium ions are not shown because they are spectator ions. They do not participate in the reaction. The strong base, hydroxide, OH-, reacts with the acid component of the buffer, acetic acid, CH3COOH, producing the base component of the buffer, acetate, CH3COO-, and water. This buffer has resisted a change in pH by removing the strong base, hydroxide, from the solution.
Okay, so that's a buffer. Lots of buffers in our body. The one I want you to memorize now, because we'll do this again when we do chapter 27, I believe, but you might as well memorize this now. Bicarb is a major buffer in our body. Bicarbonate, baking soda, but not the solid baking soda that you have home, liquid baking soda. It's in the liquid form. It's dissolved in water, in our blood plasma, in our intracellular fluid, etc. Here's how that works. Water plus CO2 in the presence of the enzyme carbonic anhydrase becomes carbonic acid. That's carbonic acid. It's a weak acid. It's not that strong. Carbonic acid dissociates into the acid, the proton, plus the conjugate base, the bicarb. Bicarb is the conjugate base. All right. Now, there's a principle in chemistry, really, but we use that principle in biology. It's called Le Chatelier's principle. I'm probably not going to spell Le Chatelier correctly. Yeah, I think I did. Le Chatelier's principle. And Le Chatelier's principle is law of mass action. All right. And what that means is if I add a whole bunch of substrate to this reaction, it'll drive the reaction to the right. If I add a whole bunch of product to this reaction, it'll drive this reaction to the left. So that's law of mass action. So if I add bicarb, it'll drive the reaction to the left. If I add protons, it'll drive the reaction to the left. If I add CO2 or water, it'll drive the reaction to the right. That's Le Chatelier's principle. Now, what is very, very cool about using bicarb as a buffer in our body is this. First of all, I can urinate out excess bicarb, or I can retain the bicarb in my body. Secondly, I can breathe out excess CO2, or I can breathe slower and retain the CO2 in my body. Now, let's say I hyperventilate, and I breathe out my CO2, and my CO2 drops. That drags the reaction to the left. If CO2 drops, the reaction is driven to the left. All right? Because I'm hyperventilating. I'm breathing it all out. Let's say that I have a hard time breathing. I'm hypoventilating. I have asthma or emphysema or something like that. I'm not breathing well. Well, CO2 accumulates in my body. That drives the reaction to the right. So you can see that my respiratory system controls how much CO2 is in my body, and that changes this reaction. Likewise, my kidneys control whether I retain or get rid of bicarb in my urine. So this is a good buffer system that you see here, and it's one of the major buffer systems we'll talk about in the future. But buffers resist pH change.